Any questions or comments or anything on the lab or anything else to begin with? Just want to bring up or okay.
Actually,
yeah.
By the way, the second part you have to
which lab?
Yes.
Yeah.
You have to make a new file after the tutorial to do your increase the time or decrease the time, so increase the cost you get.
Do you have to make a copy of your whole model or anything? Is that
make a new
No, you don't have to. No, you don't have to. So you can just edit the one you have. So obviously if you break something, then you have to maybe restart from scratch to make it again. But yeah, no, you can just edit. If you prefer just to have a copy of everything, you can make a copy of it. But no, I think whatever you have to submit is probably just a couple of screenshots. Then that doesn't you don't have to submit the models as well. So yep, that's fine. Anything else? No, okay. Yeah, people online. There's only a few of you. If you have questions, just put them in the chat. Well, it will pop up. And this has been recorded anyway. Yes, it is. Yeah, thanks. Only a very small number of people did feedback. But I'm summarizing it here. So there was, in case you weren't aware, I made an anonymous survey. Why can't this let me? Sorry, it's sometimes awkward. The cursor disappears. Okay, there we go. There was anonymous feedback that was only open for a week last week. So I just went in and just summarized. I normally do this in my modules just to see what people comments have. Though I feel as if there probably wasn't enough people for this to be statistically representative. But anyway, people thought the workload's reasonable. The hands-on aspect is good, and the flexibility people commented on is good. The notes, tutorials, TAs are all grand, people are saying. And then I guess mini projects, maybe people would like some more clarity on those and to help with those. And then to do it to quizzes, maybe some questions seem like they're disconnected from the lecture content in some way that would have that clear. And then separately, which is a fair point, that if we only have a lecture lab once at the end of a week, then if you're stuck early in the week, then it might slow down your progress a lot if you come chat about it. So that's fair enough. So for the meeting board, and so what can I do about any of these things? So for the mini projects, I might just send an announcement just to say people on Thursdays like that. I guess informally I've been doing it, just chatting with people on Thursday labs when people turn up for asking if they thought about their mini project or what they'd want to do, but I kind of left it to the student. But maybe I'll be more hands-on, so I'll make an announcement, just say, if you want to chat about your mini project, come on Thursday, I'll be there, I'll chat about it. Lecture content and quizzes. Yeah, I can look into it and see. Definitely it's something I can change for next year. Maybe I was even thinking, I just kind of ran out of time this year, that I could put for each quiz, I could say, here are the relevant lecture slides that you could look up or something like that. So you just don't have to explore the entire content to find it. And I'm more than one lab a week, but I can't change the lab structure. This semester, I can ask for one next year. But for this semester, people haven't really used the discussion forum and stuff like that. I think one person did, so maybe I might just want to send an announcement, just remind people that you can ask questions there, and myself or TAs will try to get back as quick as we can. So I know it's difficult to ask exactly online, so maybe there's some way you could maybe put aside an online hour. So I could do that early in the week. If you've got questions, they can log into that. So that's fine. Okay. Any other general comments on that? Oh, okay. I didn't upload that online, but I will upload that online. Okay, so we started with OpenFOAM yesterday. So these slides are just going to go through what is OpenFOAM, just give you some background, some historical perspective on what OpenFOAM is and where it comes from and why it looks so different. Everything else. And then we'll see how we're going for time. We might talk about meshing in OpenFOAM as well. Okay, so what is OpenFOAM and what can it do? So first of all, where does the weird name come from? It's nothing to do with simulating foam. It's just as scientists and engineers, we like coming up with acronyms, or more specifically, backronyms. We come up with a cool looking word and then try to get words to fit that. So I'm pretty sure that's what they did here. So it stands for Field Operation and Manipulation, which is perfectly descriptive and describes what OpenFOAM was not. So I guess continuum mechanics is all about fields and manipulating fields. So that was kind of where they came up with the idea from, that you're manipulating fields, and by field, I mean like temperature field, the velocity, the pressure field, they're the sort of things you're calculating. So that's where field comes from, and open here means that it's open source. The general idea, it's just a C++ toolbox for developing your own numerical solvers or using existing ones. So it's like a big folder of different types of files and pieces of C++ code that can do different things, and we're using the built-in functionality, but you could potentially develop your own. It can be used for multiphysics in general. I'm interested in solid mechanics in OpenFOAM, but predominantly it's used for fluid mechanics. Like most people using OpenFOAM, just doing kind of standard CFD problems. But you can do all sorts of multiphysics. I've seen people doing like solving magnetic, like Maxwell's equations and stuff like that, or all sorts of interesting things like that. You can see in the tutorials, there's financial, the Black-Scholes equation is there as well, if you wanted to do that. Just some history to it. So before it was OpenFOAM, it was just foam. So just field operation manipulation. There's a software called foam. So late 80s, early 90s, there's a guy called Henry Weller. He was doing a master's or PhD in Imperial College, I'm not sure. And at the time, there was a new kind of concept in programming called object-oriented, which was a new way to structure more complicated codes. And that's just been developed. So the C++ language is starting to become popular, and it seemed like a really powerful way to write softwares. Before that, everything was written essentially in Fortran. So now the only people who use Fortran are old engineers and old scientists. So I'm definitely offending many of my colleagues there, but it's true. So that's the way everything's written. And if you ever look at Fortran, it's really like if you want to do multiply a tensor by another tensor, you have to loop through all the components and like do it all component by component. Now you can't define functions, but things like object-oriented languages, they let you abstract that away. So you can almost, like you don't need to care about the individual details. You can just say, here's a field, multiply this field by another field, and you don't have to worry about multiplications. So this guy, Henry Weller, was developing all of it, and he had his buddy, Hrvoje Jacek, or Herv. So Herv was doing a PhD as well. So Herv finished his PhD in mid-90s, and if you find his PhD online, it's 400 pages, which basically described like the genesis of the main CFD solvers implemented in OpenFOAM. So the IcoFOAM solver we're talking about, it's described in his thesis basically. So the two guys said, oh, we can make some money out of this. They started their own company called Nabla. So Nabla is the Southern Triangle. It's called Nabla Limited, incorporated in England. And they started to sell foam as a commercial software. So at the time, they also sold a copy of the source code to Fluent. So Fluent were an independent company. They weren't owned by ANSYS at the time. So they're in somewhere in New England. I can't remember. Somewhere in New England in the US. So they actually just selling their own code, but they're like, well, they want to pay a lot of money just to see the source code. So they sold it to them and then continued to sell foam as a commercial software. So a lot of the early years, I think Hrvoje Jacek actually just worked for Fluent, implementing the best bits of foam into Fluent. So Fluent was Fortran when they rewrote it as C and C++. So under the hood, Fluent is quite similar to OpenFOAM. Now it's probably diverged now, but that was the general idea. So then that was a bit of a not success. Foam, nobody bought it. So the company went bankrupt, folded. That was 2004. Henry and Herv, who were best buddies, fell out, started suing each other over money. And then they said, what do we do with foam? So they said, let's just release it as open source. So they made OpenFOAM. Henry made a company called OpenCFD, started making OpenFOAM, making money from providing services like features, support, training. Herb did his own thing, had his own company called Wiki. He made something called Foam Extend, which is a fork of OpenFOAM. So then there was OpenFOAM and Foam Extend, which are both types of OpenFOAM. And then in the last 10 years, Henry fell out with his current colleagues and split again and made another company. So there's OpenFOAM.org, which is Henry's foundation version, they call it. Then there's OpenFOAM.com, it's a different company, ESI, that was the one he left. Then there's Foam Extend, which was the one before that. So there's all these forks of OpenFOAM, and there are all these different people, slightly different versions of OpenFOAM, but they're pretty similar. That's a pretty interesting story. If they could make a film of it, I don't think many people will go watch it, but I'd go see the film. Okay, So what's distinguishing about OpenFOAM? So the idea is they wanted to develop a code where you could really easily make a new solver. So like they're all just solving partial differential equations, but then if you were writing in Fortran and you want to solve a new partial differential equation slightly different, you kind of have to go in and hack like really low level code to get that to work. So they wanted a kind of a general approach, taking advantage of this C++ idea. So if you were to open any of the code in OpenFOAM, which you don't have to for this, of course, if you open IcoFOAM, the solver we're using for the cavity tutorial, you can look in the high-level C file in C++, you'll see something that looks like this. So if you know nothing about programming, you can see that this looks pretty similar to this. So okay, if you don't understand this one, it doesn't help, but if you understand this one, then you can see that this is similar. So you can see, okay, I don't know what this FEM is, but I can see there's a DDT of U, a divergence of phi U, this Laplacian of U, and a pressure term as well. So the idea is that they've written it in such an object-oriented, abstract way that you could easily just change around the high-level equations without knowing that much about programming to make new solvers. So that's the kind of distinguishing characteristic of OpenFOAM. So how is it structured? Well, it's different from other softwares that we've seen. So ANSYS Fluent. So in all that time, ANSYS went around just buying up all the companies that do CFD, so they have a monopoly on it. So now there's ANSYS, it's ANSYS Fluent. And so in ANSYS Fluent, we open up an executable and we have a GUI. And when we press go, there's just one big executable called a Fluent executable. And it just has big loads of if else, if this, do this, if this, do this. If they turn on turbulence, do this, if they turn on this. If they press calculate, solve the equations. Whereas in OpenFOAM, it's basically, they call it a toolbox because there isn't any one executable. There's an executable if you want to solve, like there's IcoFOAM, which solves those equations we saw. There's Laplacian foam, which solves a Laplace heat equation. There's many different executables. So rather than one global executable, there's a different executable for every type of problem you want to solve. Now they all share underlying code via libraries. Like they don't have to re-implement how they read in the mesh coordinates or something. They're sharing certain libraries, but at the high level they're different. And so the naming structure, anything that ends in the word foam means it's a solve. They call them a solver. It means it's solving some partial differential equations. That's kind of the notation. Anything that doesn't end in foam, like you run block mesh, that's just a utility. It's something to help set up the case or analyze something about the case afterwards. So pre or post processing utility. So that's kind of the structure it follows. If you want to look at all the standard solvers in OpenFOAM, you can go to .com, or depending on your allegiances, you can go to the .com or .org. They also have similar details, or foam extendable also as well. So for most problems that people are interested in, they have some sort of solver available to do it. So if a standard solver is not available for what you want to solve, in theory, you could write your own solver. So you can see every line of code, you can download and look at every piece of every line, because it's fully open. And that doesn't mean you do that. So 90% or more people who use OpenFOAM don't care about C++. They don't want to change anything. They just want to use it as an alternative Fluent because it's cheaper or some other reason like that. But you can, and it's more so in academia that people say, I'm interested in developing codes or new numerical procedures, and I can use OpenFOAM and I can write all of my own solvers, try things out, see if it's any good, write a paper about it, etc., etc. In industry, sometimes as well, they have very particular problems, and if they pay for Abacus for 50 grand a year, and it's super general, has all its capabilities, but they just want to solve this one problem over and over again with slight variants of it. And sometimes it's worthwhile them investing in just in-house writing their own code to do that, or just take OpenFOAM and then just customize it and solve their own problem over and over and over again. So that's kind of who might be using it. It's free to download and use and distribute. That doesn't mean it's free if you're using it in a company, in terms of you have to pay someone who knows how to use OpenFOAM. So you probably get paid all right, pretty decent OpenFOAM, you want to go to the company. So you have to balance, like, well, someone's time to use it. It's not like that's not free. And then another characteristic you'll have seen is it doesn't have a GUI. It doesn't have a graphic user interface. It's all terminal based. There was, at the time when it was Foam, they had something called FoamX, with terrible GUI, and that's why they dropped it. So they just said, let's just leave it at terminal. It's fine. You have PowerView for looking at things, and people don't mind the freedom of the terminal. And just we'll leave it to other companies. If other companies want to make a GUI, sell it, they can. And other companies do. So you can go online, write GUI, OpenFOAM, you'll find a load of them. some of them are free, some of them are free, but kind of not great, and you have to pay to get the good part or stuff like that. So there's one called Helix or Helix OS from Engis, the company called Engis. That's pretty good for certain types of problems, for external CFD problems like flow around the car. You'd be able to set that up using Engis pretty nicely. And just from learning Fluent, you can see that the guys who developed it probably use Fluent as well. But I think in terms of this module, in terms of what you get from what you get from it at the end of it, having some experience in a Linux terminal is kind of useful. I think it's if you don't like it, that's fine, you can forget about it. But at the end of it, maybe you did like it, and it might be something you want to put on your CV, and you might want the option to go in that direction. Okay, this is kind of repeating. So in OpenFOAM, there's different types of executables. So that's something you write a command. So they're solvers, and they all end in foam. They solve particular problems. So pisofoam, simple foam. So if you remember from Fluent, there was an option, a piso algorithm or syncro algorithm, how it solves in every such equation. So you can understand that they're implementing those algorithms. And then there's utilities like block mesh, check mesh, fluent mesh to foam, things like that can do pre and post processing. In this case, it ends in foam, but that's just a coincidence because this converts a mesh from a fluent format to a foam format. It's just a coincidence. And then the rest of the folder of OpenFOAM, like the actual program, is made up of libraries and tutorials. So tutorials, you will have seen in our tutorials that it just comes with hundreds of tutorials, which are models already set up with different solvers. You can copy them, run them, edit them. And then libraries, so anything that's shared code are compiled into what are known as dynamic libraries. So when pisofoam loads, for it to read the mesh, it's using the same dynamic library that picofoam uses, pisofoam, simplefoam, foam. So that's like shared code. So we don't really need to care about that for using OpenFOAM. So I briefly mentioned this about what are known as forks or variants. So OpenFOAM is licensed under a particular type of open source license called GNU or GNU GPL. So this is probably one of the most extreme open source licenses. So there are certain open source licenses where, like, I can write a piece of code from scratch myself, and I can share it to the world, and there's some licenses that I can share it under, which means anyone can just take that code, do whatever they want with it. They can make a commercial software, embed my code into it. They can change it. They can make another open source software. They can just do whatever they want. So it's fully flexible. GPL is less flexible. It means that if you want to use it in your application or build it into your own code, your code has to also be GPL. So it means that Fluent can't directly take OpenFOAM code and put it into Fluent, because that would mean that Fluent would have to also now be free. So it means that anything that is GPL, if you use it in another code, that becomes GPL. So that means that people using commercial software, it means they can't use it. It means if you're getting it for free, so you have to keep it free. That's the kind of mentality of it. There are some loopholes around that. So there's something, you might have seen something called SimScale. There's like web-based CFD or FEA. It's like you can sign up an account, you can do FEA through a web browser. And so SimScale is this company that uses OpenFOAM for CFD. So they have their own special versions of OpenFOAM, but because of this loophole, you're using OpenFOAM, but you're not really using OpenFOAM. It's not really directly embedded. So that's like a way around it. And that's because the idea of cloud computing wasn't really around when GPL was recorded. But that's the general idea. Yeah, so there's openfoam.org.com, extend, and just have a version. Caelus is another version. There's loads of different implementations. You can make one, you can download it. I could download it on OpenFOAM, change nothing about it, re-upload it on my own website and call it Phillips Foam. So GPL says that as long as I follow the other things, that's fine. I can't go into the code and get rid of people's authors' names and stuff like that. That would be against GPL. But you can do that. And you can actually sell. People are wrongly think you can't sell GPL code. You can. I can write something. If you want to pay me €1,000 for some OpenFOAM code, you can do that. You can do that. But you get all the rights of GPL with the code, which means you can give it away for free. So I couldn't make a business model around selling an OpenFOAM solver, because once a few people buy it, they'll just give it to all their friends, and then that's my business model. But actually, there's companies like Engis who have their own version of OpenFOAM, and they have cool features, and it's not publicly available. When you write something in GPL, you don't have to make it publicly available. So they sell GUIs, and then when you buy a GUI, you get their amazing version of OpenFOAM. They basically say, you probably don't want to give that away, or we're not going to sell the GUI to you again. So they kind of have, I don't know, they have ways of doing it that people don't share their version. So Okay. Yeah, last couple of just slides on the general structure of how you approach something in OpenFOAM, and then I'll go on to talk about meshing. So when you want to create a new model in OpenFOAM, it's different from what we do in Abacus or Fluent. So in Fluent or Abacus, you would just make a new model. You go like File New, and you'd have a blank slate, and then you like build it up like geometry, mesh, material, boundary condition, press go. That doesn't make sense when you have a folder of loads of files. You're not going to write those files from scratch. So everyone, and like the leading experts, Hervé Jacek or Henry Weller, when they make a model, they find a similar model, a tutorial, copy it, and change it to change the geometry, mesh, materials, and loading condition. So that's how you make an overall model. You start with an existing model, and then you just change it to your particular needs. So you basically identify the solver you want, find a tutorial for that, and then change the geometry, mesh, material properties, loading conditions, anything else like turbulence models, things like that. So this is the general idea. It's site solver, find example, copy, rename it, change the geometry, mesh, material, loading, and then edit case settings like time step, schemes, stuff like that, run the solver, iterate. So it still has the same bullet points as Abacus and Fluent, but it's just a quite different approach. And becoming acquainted with standard OpenFOAM solvers, yeah, I gave that link before. All OpenFOAM cases, you'll maybe have started to see if you've done the first tutorial. They all look the same. So an OpenFOAM model, it's not a file like all these other softwares. It's a folder or a directory, they call them in Linux. It's a directory, and that directory has other directories inside it. And it always has a directory called constant, which is where the mesh and material properties are defined. A directory called system, where things like time steps are defined, or discretization schemes, stuff like that. And then it will typically have a zero directory, which represents zero time, when your boundary conditions and initial conditions are defined. So all OpenFOAM models are basically just a folder that have at least zero constant system inside it. And if you go into any of the OpenFOAM tutorials, the tutorial folder, many times they'll have an all run script in it. So an all run script, let me just see, do I have it on the next one? Nope. An all run script, that's just a bunch of commands in a row. So rather than someone having to tell you you need to run block mesh and then run IcoFoam, it's just they put them in a script. So you just run all run, and then it runs those. So if you're inside the script, if you just type all run and enter, it will say all run command not found, because it's not a global command. So you have to go / and then the name of the file, and dot means here, / means execute this. So / all run will just run that script, and then you can see the results. And again, for the second half, then I'm just going to go through meshing. Any questions, comments? Anything interesting? Bring up? No. Okay. Yeah.
Like the other softwares, you could have like a CAD model for your simulation.
Yeah. So the final, so we have 3 weeks of labs for each. So week 9 will be the last lab week. So that's the last OpenFOAM one, 2 weeks from now. And we will do the car case we did in Fluent. We'll do that, as well. So yeah, you can do that. Yeah, it seems I can see at first you're like, well, how can I do anything useful if I'm only drawing things with like dots and coordinates and stuff? That's impossible. But yeah, most people are using it with actual real life CADs, CAD geometry. So you'll see that. So actually last year, that tutorial I had first in OpenFOAM, and then in Fluent I didn't actually have a 3D one. So one of the comments midterm was like, well, you only showed us 2D problems in Fluent. Yeah, most don't. So I just also did the same problem in Fluent. Yeah, so you can, and you'll see that. So in terms of companies using OpenFOAM, like I would regularly attend different OpenFOAM conferences, and you'd often see like automotive companies do a lot of CFD. So a lot of the big automotive companies will use OpenFOAM, but they're so big they probably just use all the softwares depending on the department. And Formula One as well, you'll often see Formula One companies, they'll do CFD, they'll be using all the different softwares with OpenFOAM as well. And then like just anywhere simulation is used, software, open source softwares will also be used. So any other comments? Okay, these slides are introduction to meshing in OpenFOAM. just because it's often a time-consuming part of setting up a model is getting your geometry, getting it in, making a mesh. And then it's just put the boundary conditions on and press go, iterate on that. So that's why I've kind of focused on this. So you will have seen this block mesh, and then the lab next week is on block mesh to get more familiar with that. So it's not that it's simple. You can make complex geometry with block mesh, and people do, but it has to be geometry that's describable by, I don't know, Euclidean geometry or some kind of simple shapes, combinations of simple shapes. So then for more complicated things, there's something called snappy hex mesh. So we're going to use snappy hex mesh then for that last tutorial to do mesh in the car. So this is the sort of thing like if an automotive company would use snappy hex mesh to generate their meshes. And then the other thing is, if you make a mesh in Fluent, you can just export it and load it into OpenFOAM. So any way you can get a mesh into Fluent, you can just export out. I haven't checked the polyhedral meshes. They're supported in OpenFOAM. I'm not sure if the converter will work. But yeah, pretty much, the OpenFOAM contains a bunch of utilities for converting from standard other CFD format meshes. So if you get them into another software, you get them to OpenFOAM. And then just ending up with how to run some example cases as well. So you're going to cover that in tutorials, but it's just a few extra information. Okay, so similar to other softwares like Abacus Mantis, there's loads of meshing options. So whether you want the squares or triangles or hexahedra or tetrahedra, and then how you want those arranged in perfect grids or like randomly or paved or all these different settings, there's similar options in OpenFOAM. But generally, we can break down the meshing related utilities in OpenFOAM into generation or conversion. So generation is they actually make a mesh for you. So block mesh. We're going to look at snappy hex mesh. CF mesh is like very similar to snappy hex mesh. It's an alternative. Foamy hex mesh, I'm not sure if anyone actually uses that. Extrude mesh is some other special ones. Then there's conversion utilities. So there's commands like fluent mesh to foam. If you give that a fluent mesh file, it will convert it into the OpenFOAM format. There's Gmesh to foam. There's an open source mesher called Gmesh. You can download for free. Comes from Mac as well, actually. And you can just make mesh in that. It's group like graphic user interface. It's just a meshing software, so you can make a mesh in that, and that will export into lots of softwares, and you can convert that to OpenFOAM as well. And there's loads of other ones as well. But yeah, standard formats you can convert as well. So there's some dedicated commercial softwares like Pointwise and Python that make software or make meshes as well, and you can convert from those. So one of the most simple, and I've said powerful here, but I guess it's for me just to demonstrate why is it powerful, because maybe all you see is the simple aspect of it. Ways to generate meshes in OpenFOAM is this block mesh utility. So the basic idea of block mesh is that your mesh can be described as a combination of blocks, and a block is a six-faced object like a cube, which is like a hexahedra, like a six-faced object where each face has four sides. It's a combination of those blocks, and where each block just has a grid mesh inside it, basically. So you can just make your mesh out of that somewhere. The sides of the block don't have to be flat, they can follow complicated shapes, but you can make your mesh out of this kind of block structure. So the way it works is that block structure is described using a particular format in what's known as a block mesh dict. It's just a file. So in OpenFOAM, when utilities have to read things from a file, like settings, they normally are called dicts, like a dictionary. So the block mesh dictionary is where the input for block mesh is defined. So produce a 3D structured hexahedral mesh. Yeah, one comment I think I mentioned if you've gone through the tutorial is OpenFOAM, they decided for you will want to run 2D models and 3D models, or maybe even 1D. So what Fluent did is they have two different solvers, the 2D solver and the 3D solver. Or at least that was the case. I don't know if that's still the case. So it literally there's someone wrote a 2D code, somebody wrote a 3D code to analyze it. So if there was a mistake in the 2D code, it wouldn't necessarily be in the 3D code. Or if they fix something in one, they'd have to fix it in the other one, because they actually just wrote 2 bits of code. OpenFOAM, they wanted to get away from that, so they just wrote one code. So 2D models are just 3D with one cell thick and special boundary conditions on front and back. So that way they didn't have to write the same code twice. That was the approach they adopted. So that's why in parity you'll see that, oh, it looks like 3D model even though it's only 2D, if that makes sense. And they use these special boundary conditions, they call them empty front and back, which tells the solver not to solve in that direction. And there's loads of block mesh examples. So we're going to go through, look at a block mesh dict to try and understand it better. So this should help with the lab for next week, where you actually have to make a block. So the lab for next week is, I think you have to make a block mesh dict for like a pipe, a T-junction pipe, where flow comes in slow from one big inlet and fast from another one. It has 4 blocks. You have to define the block mesh dict and then run the gate. So block mesh dict, it's just a text file. So if I had to ask you to come up with this, or think about, well, how could you? What's the minimum information required to actually define a mesh that's made up of blocks? How would you do that? So one way, there's a variety of ways to do it. One way is just define just give the coordinates of the corners of all the blocks. So that's what block mesh does. So it gives these list of vertices. So they're going to be the corners of the blocks. They're not the points of all the mesh. It's just of these big blocks. So we might have a block with 100 cells this way, 100 cells that way. Then a list of blocks. So if you have all these points, you have to tell it, well, what 8 points are in each block. So each block will have 8 points. So you'll have a list of blocks where a block will say it's these 8 points. And then the order of those points is important as well, because if you give 8 points, there are not an infinite way. I'm sure you can calculate the number of permutations, how many ways you can connect those to make a block. So depending on how you connect all the points. So there is the order of those to define how they're connected. Within those blocks, then you can say, well, how many cells are in each direction? You can define things like grading and bias, and the lab goes through that. So that's like, if you want small cells near one side of the block, big cells near the other side, if you've like walls in the channel, if you want small cells near the walls, etc. And then you have options to have curved edges, or edges to follow splines, or edges to follow other complicated functions. And then the last thing is what they call in ANSYS, we call named selections, which are like regions where we want to apply a boundary condition, like any inlet or an outlet. So we can't just have the whole thing called boundary. We need to actually say this is a patch called patch 1, patch 2, patch 3, or whatever. So they're called boundary patches at the bottom. So this is the format of the file. There is a link here, and it describes in detail each part. But let's just go through the cavity case first. So first, it has these lists of vertices. So all this stuff here is comments or me commenting on the right hand side. So a list of vertices. So these are the 8 vertices defining the corners of the block. The order of these doesn't matter. It's just it will when we go to define the blocks. But you can give these coordinates in any order. You just give all the list of points. But when you give the list, block mesh automatically assumes this is the first, the second, the third, or following C or C++, 0 is the first. So this is vertex 0, vertex 1, 2, 3, 4, 5, 6, 7. So later on, if we want a curved edge between vertex 3 and 4, we can refer to 3 and 4, and it is referring to 3 and 4 here. And if we make a block that's a combination of points 8, 9, 10, 15, 12, 74, then it's referring to this list here, the order. There is this global parameter at the top. This just multiplies all these coordinates. It's just, if you happen to, it's easier to define the coordinates in millimeters. You can just put like 1000 up here to scale them all. So it's just for convenience. That's global scaling. Actually, I say if we define the geometry in millimeters, we'd set this to 0.01. That's wrong. It should be 1000. Because you need to multiply. What you need to multiply to get it into meters. So actually, I need to fix that. Okay, so then the next, further down in the file, there's a section called blocks. There's only one in the cavity case, but you've got just this line repeated, basically. So they all start with hex, because it's a hexahedra. I don't actually even know why that's there. I think when they wrote it, they thought they might have other types of blocks. I don't think it actually supports any other type of blocks. So it's just, they all start with hex. And then they give the 8 vertices that will be in the block. So in this case, we only had 8 vertices, so we have to use all of them. If you, in this case, cavity, if you just add a load of points at the bottom, it won't change anything. So if a point or vertex is not used, block mesh doesn't care. It's just the ones that actually are part of the mesh are defined. So this defines the block, and the ordering this is important, how it connects it up, and we'll talk a little bit about that. Then this is how many cells in X, Y, Z. And then there's grading at the end. In the tutorial we'll go through, that's how you can control having small cells at one side of the block versus the other side. Let me just see if I have an example here. Yeah, okay. So this is to do with ordering. So I know this this block has lots of little points or lots of annotations on it. So bear with me. So the way the coordinates were defined in this case, this is vertex 0, 1, 2, 3, 4, 5, 6, 7. So when you're defining a block, pick any point in the block to start with. So normally if I was creating a block mesh pick, and I think this is how most people do it for anything anyway complicated, I just sketch out the block skeleton, if you want to call it, like based on these blocks, and I number all the zeros and ones and twos and threes of everything. And then from there, I can easily figure out how to connect up all the blocks. So you start with any point, and so we're going to start with this point down here, 0. And then you have to pick any plane and just go around a plane, and you have to go around in the right-hand rule. So if you're right hand, if you put your fingers going around the direction you're going around the points, your thumb should be pointing into the block. Okay, so if I start here, put my thumb here, I'll go that way, that'll put my fingers going this way, right-hand rule, my thumb pointing into the block. Does that make sense? Which are right hand. So if I go around like here, that defines the first points. So it just happens in this case, we've defined it such that it's 0, 1, 2, 3, 4, but like they could be any vertices, like that could be 0, 15, 17. So if I were to go back this way, then that would be right-hand rule, my thumb pointing out. So if you imagine the plane here, if you can just put your right hand on that, the direction your fingers are traveling around is the direction you should go around. So you can start on any one of these points. You can start on 1 and then just go 1, 2, 3, 0, or 2, 3, 1, 0. Or we can pick any other side plane. Like you go 4, 0, 3, 7. So any of those will be valid for the first 4 points. So that's these first 4 here. That's called plane 1. So that's like defining one side of the block. Then the next 4 define the opposite side of the block. So if we started with this plane, you can see we have 0, 1, 2, 3. Then you have to define the next 4 points as kind of like their mirror image. Such. So wherever your 0 was, what the 0 connects to should be the next first point. So 4, and then what your 1 would connect to 5, what your 2 would connect to 6, 7. So it's like you go in the same order again. So if you put your right hand there, it's actually pointing out of the block this time. So you could define any combination. So for example, this one here would also be correct and give you the same thing. So 5, 4, 7, 6. So 5, 5. Where should we go? 4, 7, 6. Yep. So we start on the top. So then right hand rule, hand inside, you have to go around that way. So it'll be 5, 4, 7, 6. Then go down here, 1, 0, 3, 2. So did this before, you can calculate how many permutations. Like you can have 8 starting points, and at each starting point you can go, there's 3 valid directions to go, I guess, so there might be 24 different definitions. I could be wrong. However, an incorrect left-hand side of the block will be 1032. So 1032, that's gone the wrong way around. And then you connect it up to here. So if you do that the wrong way, it will make the cells, but when you run check mesh afterwards, it will say they have negative 5. So if you run, it's useful if you run block mesh, that every time you make a block, just run check mesh. And if you get negative volumes, it's easier to find a block inside out. Separately, then this X, Y, and Z, they don't refer to the global X, Y, Zs. They refer to a local X, Y, Z. So this can be a bit confusing, but the very first point to the second point, that direction, that's like the local X direction for that block. That doesn't have to actually be in the X direction. It's just, that's the direction of the first number of cells. So it'll be 20 cells in this direction, basically. And then the second point to the third defines the next one. So in this case, we actually did define them in the X direction, but if you pick this block, X, oh, it actually is also in the X direction, but you could pick some configuration that they don't have to line up. So that's another place that people get stuck. If you have 2 blocks, when the 2 blocks are connected to each other, they have to have the same number of cells when they're connected. So if there's 10 cells on this one and 20 cells on that one, block mesh can't connect them. They have to be conform. Yeah, okay, here's another question. Actually, I don't think there's any valid, there's no question about block mesh valid definitions on the quiz, but that actually is a question. I'm going to flag that. I'll add those for next year. That would actually be a nice question. No way for me to check people understand it. Then let me see. Oh yeah, so this, I won't read through this now. This is just for you for revising, that it actually explains step by step how things are connected. And yeah, as I mentioned, the second is to do with the number of cells. And then this last part is to do with the refinement ratio. So to do with how like cells getting bigger to smaller. So I think in this case, it's this number represents the ratio of the last cell size to the first cell size. So if that was 5, then the last cell would be 5 times bigger, or it's 1 over that. So you'll see in the tutorials for next week, we'll go through that. And then there's even a way that you can have, rather than just one number here, you can define multiple numbers there. So you have small cells, big cells, small cells, big cells, etc. Any combination you want. And the last couple of sections, one, there's in the cavity case, there's something called edges, and there's nothing there. But if, for example, between vertex 0 and 1, we wanted to have an arc rather than straight line, so you just say arc between 0 and 1, and then to define an arc, we need 3 points. So 0, 1, and then you just give the coordinate of another point for closure. There's also options like splines and stuff where you just give a big list of like points, and it will go through all of them. So that's how you get kind of complicated geometry. So in the tutorial for next week, the lab, we actually go through this. I think you'll have to do that yourself. And then the last section to finish off is defining these so-called main selections. They're not called main selections in OpenFOAM, that's what they call them in ANSYS, but they call them patches in OpenFOAM. So moving wall here is one of the patches, so they're going to define this top wall as a moving wall, and it's defined like this. It's a wall, and then faces, these refer to the points. So in that case, there was a 0.3765 that defines the patch, and it was listed. And they're defined in a certain order, so they're defined by the right-hand rule with your thumb pointing out. So you put your hand on where the patch will be, and then you just go around, starting at any point, go around, and then you get a list of all those. That's probably not a bad place to stop. Yeah, yeah, very good. And then the next day, I'll go through talking about a bit about snappy hex mesh and how you do like complicated geometry. So very good. Thanks very much, and enjoy the weekend.